Good day, ladies and gentlemen, and thanks for joining in to our today's webinar or product demo on conducted emission, beating the limits, keeping the RCDs. My name is Holger Urban and I'm head of product management at Schaffner EMC in Switzerland. And luckily today I can present to you a comparison of different products in different configurations and a little bit of background what this is all about. Some words to myself. I started to work as an electrical engineer in the field of industrial communication devices. Afterwards, I changed to Schaffner EMC, and there was my responsibility the design of filters according to safety standards. Afterwards, I changed inside Schaffner to be a product manager, and now since 1 year, I'm head of product management at Schaffner. Looking at the agenda, I hope everything sounds straightforward for you. So first we will start with the EMC standardization and frequency range we are looking at for conducted emission. Afterwards, we will have a short look in the standard IC 61800 for adjustable speed electrical power drive systems, so-called PDS. Afterwards, filter usage and examples in the complete drive module, the CDM, which also integrates the filter. Afterwards, we will have a short look in our data sheets, how you can find the right filter for your applications. Then I will talk about RCDs and short description of RCCB types. And at the end, we will do a real measurement, EMI measurement and leakage current measurements in different configurations. So what is EMC about and what are we talking about today for conducted emission? Schaffner is mainly focusing on the frequency range between 150 kHz and 30 MHz. We are also applicable, or our products are auto adjustable and available for the frequency range between 9 kHz and 150 kHz, where usual several standards are in the work at the moment. So for example, lighting standards. For 2.5 kHz to 9 kHz, we are able to offer LCL filter solutions or just a combination of different components, for example, only L or LC or L. And this is usually used at the main site for regenerative drive systems if you want to feed back into the grid. And for lower frequencies, we are covering our the frequency range with our product portfolio of power quality products and harmonic filters. Good, so what is the power distribution system about and what are different kinds of functional blocks in it? And where does the EMI, electromagnetic interference, come from? Usually, if we are looking at this kind of example, it comes from a motor drive which converts from 50 Hertz or 60 Hertz in the US grid frequency to DC in the DC link, and afterwards again to a motor switching frequency and getting the motor to rotate to a certain amount of frequency as well. So the conversion results into losses, and these losses are faults conducted into the mains network on the grid side. And there we use grid side filters or chokes. Then we have disturbances or faults on the output side, where we can use sine wave and DU or DV and DT filters. And in between, in the DC link, there is the capability of using chokes or DC link capacitors to get rid of such kind of disturbances. So EMI or EMC filters are used in different areas of this power distribution system. They can be used directly at the drive or as a sum filter. So here, for example, this 3-phase EMC filter can be directly placed close to the drive, or it can be placed as a sum filter at the power entry of the whole cabinet, for example. And also single-phase EMI filters, usually single-phase EMI filters, can be placed in front of the control equipment to prevent the spread of interference from the control unit and system interference into the control unit. On the output side, in direction of the motor, such kind of reactors or sine wave filters are there to increase the longevity of the motor, for example, to reduce bearing damages due to ripple currents. And this is how our EMC filters looks like. So for example, we have this FN3288 or 3280. 3288 is a terminal-based one. 3280 is a three-phase plus neutral filter, where we have also busbar for higher current available. So they are used, as I said already, as sum filter at the input of the machine towards the mains, or for distributed system used directly on the inverter to suppress the spread in the system. For smaller power supplies or for smaller power ratings, also single phase filters might be applicable. And the general rule for filtering is that the filter should be as close as possible to the source of the noise. Sometimes it's not possible. Then you need to select the positioning of the EMI filter carefully. And what's also critical is the implementation of low impedance ground for higher frequency disturbance ground, which is flowing through the capacitors back to the grid or to the noise source. Good. So here are two examples of single-phase EMI filters for control logic. They are filtering the noise from the control equipment and protect against EMI noise from surrounding systems, so for immunity as well. And in general, they are, or for all EMI filters, the function is to increase the reliability of the whole system. Good. So here you can see different kinds of filter examples. So this is one filter series. For example, now here's FN3288, and it's more or less easy to read if you know where the numbers are coming from. So if we are looking at this example here, the FN3288 HVIT, this can be used for high voltage applications. So the operating voltage is higher than compared to the usual ones. Then we have the IT, which is there for isolated grounding. So this can be used in IT networks. Then we have the nominal current. Afterwards, we have a defined type of terminal, which is also described in our data sheets. And then we have a Y capacitor configuration and the discharge resistor configuration of the filter. Looking on the right side here, for example, you can see that there are different kinds of Y capacitors available. They are available in sizes that you can reduce the leakage current, for example, or if you need high performance and leakage current might not be a big issue in your application, you could also select a very big Y capacitor and get rid of camera mode noise more easily. Good. So this is how we are able to distinguish between the different models of filters. And as I said, they are modular, and in our datasheet you will find also insertion loss curves or the performance plots of all different C configurations for all different filters. In this family, it's a little bit special. We have this FN3288 in the family, but also FN3287. FN3287 is the standard performance version, and FN3288 is the enhanced performance version of the filters. Now we are already coming to the RCD or residual current device and leakage current. RCD is clear what it is. So it's a residual current device which measures the residual current on the earth and disconnects the system in a failure. So RCCB means residual current operated circuit breaker without integral overcurrent protection. So there are different sensitivity types of RCCBs. 10 milliamp are associated with highly sensitive equipment in high risk areas such as school laboratories and in hospital areas. So they are not so super common, but still there is an application for them. Then we have the 30 milliamp, which is the typical value for just residential buildings or home appliances, let's say. And then we have the 100 milliamp and 300 milliamp purposes is to provide fire and equipment protection. So for the others, it's really about saving human lives, let's say, when touching the installation. For the others, it's about trying to prevent that the fire breaks out at the end. So there are also higher milliampere ratings available, which all have the same function as mentioned above. So all of them are there to try not to get any kind of factory burn or something really critical when someone touches the installation. So for several 100 milliamps, it's already a little bit too much for the human body. So yeah, these are the functions there, or the different categories. We will now look at 30 milliamp, 100 milliamp, and 300 milliamp more in detail. Even in the measurements, it's all about this kind of different levels. Usually the tripping of RCDs in a system is caused by high leakage current due to complex system setup, which means if you have, for example, a huge machine where you have different kinds of motor drives, which all are which all are driving different motors, they all create a certain amount of leakage current because they have a Y capacitor in them, which is connected to protective earth. And then we have some current flowing on protective earth. In addition to these complex systems, if we integrate EMI or RFI filters in the system, the leakage current is also rising for the whole system because the EMI filters will also add additional leakage current due to the Y capacitors to the system. And yeah, this might get your RCCB tripping every time you switch on the machine. And this needs to be reviewed before you connect the machine to the grid or before you try to find the right RCCB for your application. Okay, good. I think this is all for the understanding of RCCBs. If you have further questions on the design of EMI filters, you can come back afterwards and ask me or ask our people or our team at Schaffner EMC how we can help to get your system running and, for example, create a low leakage current filter or different kinds of leakage current applications. Good. So Y capacitors, as I described before, are conductive for fault currents to earth. So the common mode. Common mode means that on all lines we see a common signal flowing in one direction. And this is why the Y capacitors help. If you, for example, look here, common mode would be you have a disturbance here and the same disturbance on this line and the same disturbance on this line. And all these three are then combined force in here and will flow back to the grid or to the disturbance source on the protective earth. In our datasheets, we present usually the calculation of leakage currents according to the IEC standard. So the IEC standard for EMI filters is IEC 60939-3 at the moment. This is also harmonized with the UL standard now. In the past, we had the UL 1283, which we were following. Now we are following UL 6939 as well for UL. And this calculation is mainly used to compare filters between our different ranges, and also maybe if you have a competitor, you want to select a filter from these values are usually also collected according to the standard. It might be different in the application, and you will see this directly afterwards in the measurement. Here to say that the grid frequency is for the calculation the only frequency we are looking at. So if we are looking at this frequency here, this one here, this is the grid frequency of 50 or 60 Hertz, and it heavily depends on the application behind which the real or how the real leakage current might look like. At the end, if you have switching frequency at around 2 kilohertz, you will also see a spike there, and depending on the EMI filtering, this might be big or not. You will see this afterwards in the measurement. It also depends on the cable length, the shielding of the cable, and the switching frequency I already mentioned. To overcome problems in the application at the end, it's necessary to take measurements of the whole system and really do this carefully, that you don't have any tripping or any problems with RCCBs in the system. The circuit breaker always measures the complete system and can be selected according to different trigger currents, as I said before. So this is the one of the different analysis we are able to do with our measurement equipment at the moment. And you will see this later on directly related. If there is a green light in one of the RCCB types, then it is okay to use it. And if there is no green light, you need to select a different one with higher values. And now we will look at the EMI and leakage current measurements in different configurations, as I said in the beginning of the webinar. And we will see different configurations, which I will list on the next slide. This is the setup we did. So there is a drive where we are looking at, and so this is the drive here. Then we have close to it our filter. We will use different kinds of filters in this application example. Everything is connected to a conductive plate here, and we have a listen connected to it, artificial network, where we connect our measurement receiver here. Then we have a motor underneath the table here and different cable lengths. As you see here, this, for example, is the 5-meter cable length, and then we have one motor with 25 meters. So this is a 25 one. Also, in our test setup, we will do different kinds of shielding. So once we will have the motor, the drive side disconnected from the shielding, another measurement will be with the motor side disconnected from the shielding, and a third one will be without both. So we will see different kinds of measurements here. This mainly has an influence on the EMI disturbances in the system, but you will see this later on. One additional test is with different switching frequencies in the drive. So we are going to change from 2 kilohertz to 5 kilohertz and to 8 kilohertz and show you different kinds of measurements for this type of motor switching frequency changes. You see the basic setup of our measurement EMI receiver. First, we need to select different kind of the limit lines for C1 class to take the measurements according to EN 61800-3. First, it needs to be loaded. Afterwards, we need to set up all the different details of the measurement. So if we scroll further down, we can see different parts in our signal path. So we have the EMI receiver on the left side, we have the signal path in the middle, and the listen on the right side, and the design and the test on the right side, on the most right hand. And then we need to add a constant of 10 dB to our signal path to get the attenuation at the end right of our measurement. This measurement here is the initial measurement of our setup. So now we have no filter attached to the system, and you directly see the disturbance here, which is pretty high. So we are at roughly 120 dB microvolt, and for the upper frequency going down as expected, but also there we are above the limit for the whole measurement. Once the measurement is finished, our measurement receiver or our EMI receiver is going to take additional measurements to see where the peaks really are. And yeah, for this measurement, it's not really tricky because all of them are quite above the limit. Here you can see the leakage current measurement, first all different frequencies, and now we're going to have a look on the frequency analysis. Here you can see easily the different devices for RCCBs, for example. Now we are going to select the DFS 4B for 30 milliamp. And you see now the curves, the blue curves which appeared are the limit lines for this RCCB. And if we are scaling down to a certain amount of milliamp, you can now, or would be able, if we switch on the motor, which we are going to do soon, you can see different leakage currents around. What you also see here is that for the lower frequencies, so for 50 Hertz, for example, the leakage current is not too high, but for the switching frequency of 8 kilohertz, it's pretty high. And this is sure because, or clear, because we didn't add any filter so far, which add leakage current to the lower frequency as well. This measurement here shows the leakage current measurement of a drive when we switch from 8 kilohertz to 2 kilohertz switching frequency. And what you also see here that there is still no filter attached because we still don't have any additional leakage current at 50 Hertz. So now we added a filter in the system, and the golden measurement you see on top is the initial one, which changed now from green to blue without a filter. And now we added an FN 3288 10 amp C34 filter. And you see, this is German, sorry for this, but it says that all measurement points are below the limit, so there is no need to do an additional measurement at the end because all peaks will be below as well. And here you can directly see that the filter is working pretty good, and all the different measurement points are really below the limit, even about 20 dB microvolt below the limit lines. So our filter would pass the measurement now, or the measurement, the EMI measurement will be passed with our filter because it's below. And the setup here is now a 2 kilohertz switching frequency with the 5 meter cable length and both shields attached to the system. So now we are taking the measurement again without the additional measurements in it from the past measurement. And as you see, still below the limit. And now we are going to take a deeper look in the leakage current measurement of this system. So yeah, as we said before, we are still below the limit, about 32 dB below. And now we are switching on the leakage current measurement. Here you can see the effective diagram, and now it changed from 2 milliamp to 38 milliamp in the whole signal. But for the lower frequencies like 50 Hertz or 150 Hertz or 300, it's still below, or it's still very low, below 1 milliamp. And for the higher frequency, it changed a lot. So it's there even higher than before. And now if we are looking at the frequency analysis and adding the limit lines for the RCCBs in it, we will also directly see that it's okay. It's not the RCCB will not react on this leakage current, but it's higher than before. And what we also see here is that we have now added leakage current in the lower frequency spectrum. So here we have just as the highest frequency, more or less the 2 kilohertz switching frequency, which we saw before. But we also see additional peaks for the 50 hertz here, for example, or the 150 and 450 as well. So these are the multiples of the 50 hertz grid frequency, which we see now in the leakage current. 150 hertz is around 5 milliamp, which we saw already in the last measurement, but here you can see really the peak where it is, and yeah, it's still below the limit, so we still have around 75%, which could be on top of this peak before the RCCB breaks. And to visualize this even more, there is another function in our system where we can just show, based on the different kinds of RCCBs, which would break or which would do circuit break. Now you see this here, so we have 25%. This is in percentage. We have 28 or 27% of a 30 milliamp loaded. We have 50% of 100 milliamp and 10% of 300 milliamp RCCB. So there is a lot of space, let's say, to the limits above before we need to change to a bigger one. So now we are looking at different kinds of shielding attached. What you see in the green and blue is the old measurement which we saw before, and now it changed again to green and blue, the peak and average measurement, and we see now this is the measurement without shielding on the motor side. So it changed quite heavily for the upper frequencies. This measurement here shows the measurement with the no shield attached. So the shield is still on the cable, but it's not attached on motor side or on the drive side. And then it's even higher in the higher frequency ranges. So yeah, to understand this or to make a point here, in general, a shield is like a capacitor, which is close to the lines, the power lines, which are in the cable. And if you attach it to the different sides or not attach it to the different sides, then the capacitor is not formed properly and will induce even more problems in the higher switching frequencies. And if it's connected properly, it works like a small capacitor and will mitigate disturbances in the higher frequency range. Here we can see the last measurement in this range of tests. So now we have connected the shielding on the drive side again, on the motor side again, sorry. And now it's disconnected on the drive side. And the picture is more or less the same, but a little bit different. So it's just to show you that it depends a bit on which side the shielding is connected. It's best way just to connect it on both sides to have a reasonable disturbance limiting effect of the shielding. So this measurement now shows the difference when we switch to a different frequency, a switching frequency, a different one. In the past measurements, we always did it with the 2 kilohertz measurement, 2 kilohertz switching frequency of the drive. Now we change to 8, and with the 8, it's different as well. So we are closer to the limits, but still below. So now we switch to the leakage current measurements. You can directly see with the red cursor that the switching frequency is now at 8 kilohertz, as I said before, and the leakage current measurement looks completely different than before. Before we had a higher peak at 2 kilohertz, and now we have a peak at 8 kilohertz. So in total, for the whole signal, it's even below the one before. And also for the higher switching frequencies, it's always the same. So it will be reduced because the filter attenuates even better for higher switching frequency or higher frequencies close to the resonance frequency of the filter. And here we also see that we have more or less the same amount than before for the RCCB in percentages. So now we will do a measurement with a different filter type. This filter type is an FN3288 as well, but with the lower leakage current, so with lower Y capacitor values. And this we will directly see in the lower frequency range. So for example, at 150 kilohertz, we are above the limit of some dB. So I think it's around 5 to 6 dB, what we will see now as well in the measurement below. And we are not able to pass with this filter, but we need to think about that this is the most severe level of limits, a C1, for this kind of applications. And here we directly see what the filter is capable in doing. So it does not add leakage current in the lower frequency range. So for 50 Hertz or 150 Hertz, there is no leakage current left, more or less. But for the switching frequency at 8 kilohertz, we will directly see that there is a big peak, and also the multiples of this switching frequency is visible in the spectrum, which was not possible before. When we now look at the different curves of the RCCBs, it will be clear that all of them are stable. So we will have a look now first at the effective diagram, or the we are looking at the percentage of RCCB, how they are loaded right now. So all of them show 24%. And once we took the measurement, we were a little bit wondering why this is always 24%, but looking at the different kinds of curves, according to the models, they are all stable in the upper frequencies. So everything above 2 kilohertz is stable, and the same for the 300, the 100, and for the 30 milliamp RCCB. So this is why we opened up again and thought, why could this be? But in the next few seconds, you will see the differences in the range of above 2 kilohertz. So this is visible here. You can see it directly here. Now we added the curves, and the 30 milliamp is the same as the 100 and the 300 as well. So now we can see one of the next measurements where we attached the 25-meter cable length to our drive, and we changed back to the high performance version, so the one with the higher leakage current. But we are still below the limits for 25 meters and class C1, which is pretty good for such kind of standard filter and the surroundings we are in at the moment. Leakage current measurement of this system also now shows no big difference, let's say. So it's still the same, not really depending on the cable length. We directly see the 8 kilohertz there. The red cursor is right now. And also, like before, we see higher peaks at 50 hertz and 150 hertz, 450 and multiples of 50 hertz. And looking at the effective diagram, it's still the same as before. So we are still below the limit, and for higher frequencies, we are at around 20 milliamp as we were before, and stays the same, not really depending on the different cable length. Also, the type percentages are still below the limits, 28%, 14%, and 8%. So, for example, if we use now 8 drives in the same configuration, and we want to select an RCDs according to this, we need to select the 300 milliamp one, because 8 times 8 is still below 100%, but for the others, 8 times 14 will be above 100%. So we will see a different, or the RCDs tripping. As one of our last tests, we switched the filter type again. Now we are looking at the 3287, also with the high leakage current version. So it's also, I think, a C34 or 35 version. And here we are above the limits a bit in the lower frequency range. But yeah, we still need to make ourselves clear that this is still C1 and it's a standard performance filter with 25-meter cable length. So also there, I think we have a pretty good product. And in the higher frequency range, we can also see that the performance is quite good, and we are far away from the limits. So that's it for today. I hope you enjoyed the presentation of the different measurements and the different filter types we are using for this kind of measurements. If you have any questions, don't hesitate to contact me. You can either write an email to info@schaffner.com or to myself. My email address is holger.urban@schaffner.com. Thank you again for attending, and enjoy the rest of your day.